Okay, so today we're getting into optimization, which sounds very fancy. Very fancy way of saying that we're trying to minimize or maximize something. We want the optimal value of something, which sometimes means that we want it to be the least, sometimes we want it to be the greatest, but basically we're looking for a relative min or max for our function. We're just in the real world. So we're going to look at some different types of functions we might end up with and how to decide, are we looking for a relative min or a relative max? And then we will be using calculus, finding the derivative to find that min or max. The 4 examples that I am about to go over, they are word problems. So if you want to print these or type them out or something, they are posted along with this video. But otherwise, I guess you could have in your notes, refer to example 1 or write down at least the gist. For most of these, there's some sort of diagram that you can draw with them, so you could kind of draw the picture to give yourself the idea of the question in your notes. So our first example has a rectangular page. Most pages that I know are rectangular. Contains 24 square inches of print. The margins at the top and bottom of the page are to be 1 inch, and the margins on the left and right are to be 1 inch as well. What should the dimensions of the page be so that the least amount of paper is used? Okay, so first, giving ourselves an idea of what this is talking about, I'm drawing my page, and they're talking about the middle part of this being that 24 square inches of print. So this is my 24 inches squared. But then the margins on the top so my margin around this side, the bottom, I can draw that here if I wanted to again to talk about the bottom and the right side, but my margins all around this are 1 inch by 1 inch for the whole thing. So this is the idea of what we're talking about. We are looking for the dimensions that are going to produce the least amount of paper being used. So they're saying if we want 24 inches of print, what should the overall dimensions of this piece of paper be? That way we are using the least amount of paper. So let's go ahead and get some variables in here. We don't know what our x and our y will be as far as I'm looking at the dimensions of this inner part, my x by y. And I'm looking for the overall dimensions to be the smallest, but that also means that x and y are the smallest for what they're talking about. So what I'm looking to minimize, first of all, if we're talking about the area of this piece of paper, that means we've got this x value, but then we have the margins on either side, so my length and my width. My width here being that x plus 2, and my length or width, it really doesn't matter which one is which, my height really being y plus 2, my margins on either side. And this is the area that I am looking to minimize. So eventually I will be taking the derivative of my area, and I'm looking to minimize the area. The trick to optimization is that if I'm going to find the derivative of something and look for the minimum value, or where that derivative changes from negative to positive, that means I need to only be looking at one variable. So where for implicit differentiation, if we were doing related rates, it really didn't matter whether we substituted things later or not. For this, I do need to have it an all one variable before I start. So I'm looking for what other information do we know from this, and the part that we haven't used is at this inner part. The area is 24, so that means the area of the inner part would be x times y is 24. So I can solve for a variable, and I'm going to solve for y so that I can replace y and be in terms of x. I just prefer being in terms of x. It really doesn't matter for this. We can have it in terms of x or in terms of y. So my y equals 24 over x, so that way I can replace my y with a 24 over x. And now I'm allowed to find a prime. I could multiply this out before or after I find the derivative for this one. I think it is a little bit easier to multiply beforehand, but it doesn't matter. Just if you start to find the derivative right now, we would need to use the product rule. I'm going to go ahead and distribute because I know when I multiply my x times 24 over x that that's just 24. And so that's kind of nice. I get a 2x. And then when I distribute my 2, I have a 48 over x. And then distributing my 2 there, I get 4. Okay, so now this is a little bit easier to find the derivative of. And with my constants, my 24 and my 4, I could combine them, but we know when I go to find the derivative that they're going to go away because the derivative of 24 is 0, and so is the derivative of 4. So I just have the derivative of 2x, which is 2. And then my 48 over x, remember that's like 48x to the negative first. I will end up with a negative 48 x to the negative second, or over x squared. I am looking for where this a prime is 0, so it does help to, it's necessary to get a common denominator so that when I set it equal to 0, it's easy to solve. So I will need to multiply this 2 by x squared over x squared. And now when I set that a prime equal to 0, I only have to worry about the numerator, because when I cross multiply, that x squared is going to go away. Making sure I have enough steps here. So let's see, we can factor out, we won't factor anything out. We'll get our 48 to the other side. As we could factor if we were just really wanting to. Dividing both sides by 2. And then we get the square root of 24, or plus or minus the square root of 24, which is about 4.899. Remember, for AP Calc, we're rounding to 3 decimal places, whether you're rounding there or truncating. And then we do have a positive or a negative. We know that one of those is not going to make sense, usually the negative. But we're going to go ahead and analyze our a prime here to show why we know which one works and which one doesn't. Remember that we're looking for a minimum. So if we had to justify our reasoning and why it was the minimum, we would have to say something about a prime going from negative to positive, that it went from decreasing to increasing. And because a is, so it's not just a parabola, we have that denominator involved. So I want to look back at my a prime, and I am going to test values. So at 0, I will have something about it's undefined at 0. If I plug in 1, I'll get a negative in the numerator, positive in the denominator. If I plug in 5, let's see, we've got 50 there, so positive over positive. And then a negative 5 would be positive over positive. And we can see that for a prime, where it goes from decreasing to increasing, is at 4.899. So this is where we have a min. We always want to go back to what they were actually asking us, because the original question was, what should the dimensions of the page be so that the least amount of paper is used? So this was the minimum for the x value. So when I go to say the dimensions of my paper that will minimize the amount of paper being used, still having that 24 inches squared in the middle that we can write, would be my 4.899 plus 2 is going to be the width. So it's 6.899. And then for my y value, I do have to go back to the fact that x times y has to equal 24, or that y equaled 24 over x. So my 24 divided by 4.899 is going to get me that y equals 4.899 as well. It's a square. So it's going to be by 6.899 as well. That was, not necessarily coincidence, but just the way that minimizing paper area is going to work. But always if we have two different dimensions going on, we're plugging back into whatever we know to be true to find the other one. Just happened that these were the same. Okay, so that was minimizing paper. Our example 2, we're finding the point on this function that is closest to the point 2, 1. So a little less wordy. But we still have a picture that we can look at with this. We're talking about the graph, the square root of x plus 1, so it's been shifted up 1. There's the square root of x plus 1, and then the point 2, 1. Maybe something like that. And what this question is asking is, what is this point that is closest to my point 2, 1. So we're saying, what is the minimum distance, or the point that is the minimum distance. So since we're talking minimum distance, that means we want to consider the distance formula. Couldn't decide how I wanted to write that. And in this distance formula, I know that one of the points is 2, 1. I just don't know the point that is going to be closest to it. So I can plug in my 2, 1. Doesn't matter which part of it I use here. As long as it's the first number in both or the last number in both, but 2, 1. And now, again, before I take the derivative, this is not related rates, so before I take the derivative, I do need to have it all in terms of x or all in terms of y. I always prefer terms of y, and that's easiest for this one for sure, because the y value I know I'm talking about for my function f is the square root of x plus 1. I don't necessarily know what the numerical value of that is, but I know that whatever x is, y has to be square root of x plus 1. Be careful, I can make it long enough. Be careful that that whole part is in parentheses because we are subtracting. And again, this is going to be a situation where it will be easier to simplify before I take the derivative rather than taking the derivative of this. So we've got that 2 minus x squared will be a 4 minus 2x. Oh, that's not right. 4x and 4x. I guess I could have combined like terms afterward. Plus x squared. And then over here, I'm missing a parenthesis first of all. 1 minus my square root of x, and then minus 1, so my 1's will subtract to be 0. And then I'm left with a square root of x, negative square root of x, squared. So that's nice. And I'm almost there. So this part, my negative square root of x squared, is just x. So that means that I have a negative 4x and a positive x. So I'm left with x squared minus 3x plus 4. Okay. So now I'm in a place where this is much easier to take the derivative. So my distance prime, d prime. I'm using the chain rule, so I've got a 1/2 everything that's underneath the radical, all raised to the negative half, and then multiplying by the derivative of the chocolate, so 2x minus 3. Cleaning that up a little bit, we get our 2x minus 3 in the numerator, my 2 square root of x squared minus 3x plus 4 in the denominator. But again, when I set that equal to 0, my numerator is really the only part that is going to count for anything, so I'm going to go ahead and take that part off since I'm running out of room. We get 0 equals 2x minus 3, and then our x will equal a 3/2. So again, for this one, I'm only getting one value. That last one we had 2 values, but only one that really made sense as a dimension. For this one, we only have one value, but we just want to make sure that it makes sense. So if we go back to our d prime, if I'm plugging in 0, then I'll have a negative in the numerator. Let's see, 0, 0, positive in the denominator. If I plug in 2, I would have positive in the numerator. Let's see, you'd get a 4 and 8, and that would be negative 6. So positive in the denominator. So if we needed to justify ourselves, we could say that d prime goes from negative to positive, so it does have to be a relative min. We were looking for the point that was closest to 2, 1, so this is going to be an ordered pair. So in the end, this was our x value, 3/2. And then we're just plugging in our 3/2 into our function f of x to see what that ends up being. So I'm just going to use a calculator. If we didn't have a calculator, we would leave it really gross. We would just say square root of 3/2 plus 1, whatever that is. But with the oh, I don't think I typed that in right. Square root of 1.5. This one. That's better. We get about 2.225 or 224. So this is the point that is closest to the point 2, 1. And we can see that this is pretty close. This would be like 1.5, and then we would have to get a 2.225 when we plug it into the function. Always good to start with a picture because that tells us, in this case at least, that we were close to a right answer, that it at least made some sense. Ooh, I'm gonna need another piece of paper. It bled through pretty good. Okay, so example 3, we're talking about an open box with a rectangular base is to be constructed from a 16 by 21 piece of cardboard by cutting out squares from each corner and bending up the sides. Find the dimensions of the box that will have the largest volume, and look at almost underlined the part that we need to look for. So this is one that we are looking for a max. We're looking for a largest volume this time. This is a problem that we dealt with in pre-calc, but we had to use our calculators for it because we couldn't find mins or maxes without a calculator if it wasn't a quadratic. So to give us an idea of what this is talking about, we've got this piece, what did it say it was, cardboard? We've got this piece of cardboard that is a 16 by 21 to start with. But then in order to make it into a box, we're cutting out squares in the corners and folding up the sides. What they're asking is what the dimensions of these squares would need to be, which they are squares, so it'll be the same dimension, 3 by 3, 2 by 2. What those would need to be in order for the box that's created to have the maximum area. So the box that's created here since this was 16, the width was 16, but now we're going to be cutting out an x from either side in order to fold up the sides. So this height ends up being x, that's how we're folding it up. So that means that my width ends up being 16 minus 2 x's. So we don't know the length of each x, so I don't know what it ends up being, but I do know it's 16 minus 2 x's. And then very similar for the length, that it was 21, but we're cutting out an x up here and an x down here, so that length ends up being 21 minus 2x. So volume is length times width times height for a rectangular prism. So in our case, our volume would be, the length is 21 minus 2x, my width 16 minus 2x, and my height of x. So this is the first problem that we don't have an x and a y involved, so I'm good on that front. I don't need to plug in anything else, which is good because I've used all my information. I am looking at taking the derivative and looking for my max of x that gives me the largest volume. But this is going to be easier to find the derivative if I don't have to use, I kind of have two different product rules going on. Or you could distribute at least one x and then use the product rule. I think that would be a little bit easier. If you're going to multiply this all out first, I'll show you that way, and then if you choose to use the product rule, just you can do it. Good luck. You do want to distribute the x first, or you can multiply these first and then distribute the x, but you need to multiply two things at a time. So we're not trying to multiply all three, that's not going to work. But I could distribute my x in, get a 16x minus 2x squared. And then I can use FOIL or multiply my binomials here, where I'm distributing my 21 to both, and I'm going to get some pretty big numbers here. Got 21 times 16, so 336 x, multiplying 21 times negative 2, so negative 40, 2x squared. Got my negative 2x times 16, so negative 32 x squared. And then my negative 2 times the negative 2x squared is a positive 4x cubed. Okay. So rearranging some things, combining like terms, I've got my 4x cubed. In the middle, I've got a negative 74 x squared. Okay. So that wasn't a ton of fun, but it is going to make taking, my handwriting's going that way. It is going to make taking the derivative so much easier, because now I can just use the power rule, and sometimes it's worth it to make the calculus part a little easier. So now I can just use the power rule, my 12x squared minus, let's see, 148 x plus 336. I am looking to maximize, so I'm looking to set this equal to 0 and solve. Let's see, can we divide them all by 12? I don't know if they're all divisible by 12. No, 148 is not divisible by 12. Let's see if it's divisible by 6. Nope. So I think the highest we're going to be able to factor out is a 4. Yeah, but I can factor out a 4. Better than nothing. Let's see. Okay, and then from here, this might be factorable, it might not, but I still have pretty big numbers, so I'm just going to go straight to using the quadratic formula that I know my x is going to equal negative b, so negative 37 plus or minus my square root of b squared minus 4 times a times c all over 2 times 3. Okay, it's been a while. I would go ahead and simplify what you have in parentheses. The square root of 361 for 6. So we have one of our answers being 37 plus the square root of 361 divided by 6. So a 9.33 repeating. And then one of our answers, a 37 minus the square root of 361 divided by 6. So it looks like this was factorable. So you could definitely factor that if you wanted to multiply your 3 and 84 and look for factors that multiply to be that and add to be negative 37, break up your middle term, but I just think quadratic formula with that big of numbers, it's going to take me a while to think of it, so I thought that was just as easy. Okay, so we do have two different values, so we have to figure out which one is talking about the max. So we've got a 3 and a 9.333. That we are talking about volume prime, V prime. So for our volume, this one, our V prime, it is quadratic, so this is one where I can just use what I know this function to look like. I don't have to plug in anything, and it is a parabola facing up. So I know that b prime is positive, and then negative in the middle, positive on the end. So if I'm looking for the largest volume, or the x that would maximize volume, I'm looking for where my slope goes from positive to negative. I want that max. So my slope going from positive to negative. So that means that my dimension of x equals 3 is going to be the max. But we're looking for the dimensions. So that means the dimensions of my box are going to be a 3 by, 16 minus 6, so 10. And then 21 minus 6, 15. So these are the dimensions that will maximize my box. If I cut out a 3 by 3 square, and then my box is a 3 by 10 by 15, that is the maximum volume I can get out of it. Okay. So the last question we're looking at, the page before it bled through pretty bad. So we've got a gardener that wants to construct 4 garden areas by first building a fence around a rectangular region, then subdividing the region into 4 smaller rectangles by placing 3 fences parallel to one side of the rectangle. So pause. Let's look at what this is talking about. We've got a rectangular region to start with. Surely you guys heard that. That was real loud. Why is he barking right back there? Okay, so this is our rectangular region to start with, and then he's dividing it into 4 smaller rectangles by placing 3 fences. Let's see if I can do that correctly. Okay, so here are my 3 fences. I ended up with 4 rectangles. They don't all look the same, but they look close enough. Parallel to one side of the rectangle. Okay, so that's the scenario we're talking about. Big fence, rectangle, and then we've got 3 fences in between. It wants to know what dimensions of the region minimizes the amount of fencing if the total area of the region is 300 square feet. So we've got that the area is 300 feet squared. And to me, this one makes the most sense. Well, the last one was good for maybe if you're shipping products, you want it to have the maximum volume for the minimum amount of, or see what would maximize the volume for how you could cut your boxes or something like that. And this one makes a lot of sense to me, where if we had a limited amount of fencing and you're trying to fence some sort of animal in or something, that we would want to have the maximum area for this animal but use the minimum amount of fencing. So that we're spending the least, getting the most for our money. So we know our area is 300 feet squared, but we're trying to minimize is the amount of fencing. So if we're going to talk about the amount of fencing, that means that we have to look at the dimensions we're using for the fencing. So if I call this part x, these would all be x because those are all the same length, and then this could be y, and that would mean that this is y down here as well. So if I'm using all of this fencing, that means I ended up using 5 x's, and 2 y's. That's how much fencing I ended up using. This is what I'm going to be minimizing. I want the minimum fencing. Always identify whether you're looking for a min or a max and of what. We're looking for the minimum fencing. And in order to get them in terms of each other, I have to look at the fact that this is my constraint. The area has to be 300 feet. So I know that since I called this x and this y, that 300 would have to equal x times y. Similar to one that we did on the front, that I can get this in terms of x by solving for y and replacing it. So my y will be 300 over x. And then I can replace that. We've got 2 times 300 over x, or 600 over x. And I could get a common denominator before I go to find the derivative, but it's not going to be any easier because my common denominator would just make me have to use the quotient rule. So I'm going to go ahead and find f prime. end up with 5. And then for my 600, x to the negative first, actually end up with a negative 600. And then x to the negative second, which is over x squared. Now I do want a common denominator because I'm looking at setting it equal to 0. So this is where I'll go ahead and say f prime equals, multiply my 5 by x squared over x squared. And then when I set it equal to 0, my denominator is not going to make a difference. I'm getting my x by itself. Oop, don't want to lose my 5. I'm getting ahead of myself. So I've got 120. And then taking the square root of both sides, we get, see, about, using about simple, 10.954. So if I needed to look at this, plus or minus. So it's like that first one where I do get a negative, but it's not going to make sense for this problem. If I'm looking to minimize this fencing, I can't have negative fencing. That would sure minimize it though, if we had negative fencing. This is a parabola f prime. Well, sorry, we don't want to go back to this. We want to go back to the full f prime. So this is one that you'd have to plug in values for, since it is rational. We could plug in, well, 0 is undefined. I did that on the last one too. We would plug in 1, we would get a negative in the numerator, positive in the denominator. If I plug in, let's see, 20, I'll end up with positive and positive. If I plug in negative 20, positive over positive. And we're looking for the minimum amount of fencing, so I'm looking for where it goes from negative to positive. So that's my 10.954. If I had to justify it, I would say that f prime went from negative to positive. So I'm talking about my 10.954. In the end, we're looking for what the dimensions of the region are, so my x by y. That minimizes my amount of fencing. So my x is already good, that it will be my 10.954. But then to find my y, I'm taking 300 and dividing by my 10.954, and I get 27.387. And this was talking about feet. I don't think I said on my last one that what we were dealing with was inches. But. So the big things here are, first of all, deciding what you're minimizing or maximizing, that you come up with a formula. Sometimes it can be an area formula. Sometimes it's just going to be you creating an equation that we're talking about. So in this case, it was the amount of fencing. Deciding if it's looking for a min or a max. Then if I need to replace anything, so for this I had x's and y's, I need it all in one variable, terms of one variable, so I can use any other constraints to replace that x or y. If I need to simplify it before taking the derivative, like on this one, simplifying it can make it easier, but if I wanted to just distribute the x and then use the product rule from there, if I'm feeling bold, go for it. And then in the end, we always want to justify that we are looking for the min or the max, looking at how the signs change on that prime, whatever we're talking about, the derivative, and then making sure that we answer the question. So if it's talking about the dimensions of something, we go back and actually find what those dimensions were. All right. So you've got a few that are similar to this in your homework. If you've got one that's a little bit different, try it out. Don't give up right away. Start with a picture. See if you can picture what it's talking about. Decide what's minimizing or maximizing, all the things that I've talked about here. So, anywho, you can do it. Enjoy the rest of your day.